So what I'll work through just a little later is the general problem solver algorithm. This is an algorithm that originates in 1959, originally by Simon, Shaw, and Newell, and it was part of really like the very, very beginnings of AI as a field. And people said some very enthusiastic and what now looks to be pretty foolish things about the capabilities of this general problem solver algorithm. So they thought it would be an algorithm that would solve really any problem, hence the general in its name. As it turns out, it's really quite bad at solving any problem. It's very, very vulnerable to what's called a combinatorial explosion, which makes processing problems just computationally untenable. It'll become too expensive, take too long, whatever. So how it works is it's based around the idea of means-end analysis, something first put forward by, I think, Aristotle. So it works by saying, okay, so I need to get out of my house. So you'd go, okay, so currently I'm in the, I need to get to the door, and I'm currently in the kitchen. So to get to the door, I need to leave the kitchen, and to leave the kitchen, I need to walk. And maybe to leave the kitchen before I start walking, I need to drop whatever I have in my hand. Maybe I put the pot down so I don't take it out of the kitchen. So it's just like sort of figuring out what do I need to do to get to there, and what do I need to do to get to there, and what do I need to do to get to there. So it's sort of a chain of actions that should eventually link up to the end goal is the basic thinking behind the general problem solver algorithm. The reason it becomes awful at doing difficult problems and a variety of problems is the way in which it organizes the set of possible actions and determines which of them to use and which of them to use in which order. I'll explain that a little later, but basically the idea of having a token, and you can say, okay, this is an action, and associated with that action, say putting down the pot, you have a number of states. You have the states that need to exist before you can do that action. So these need to be the current state. So for instance, if you want to put down the pot, you have to be in the kitchen because you don't want to put down the pot in the living room. That would be a mistake. So you would have, before I can put down the pot, I need to be in the kitchen. But also before I need to put down the pot, I need to actually be holding the pot. So this is another current state. So you'd have the set of current states. These need to be active before you can perform that action. Then you have a set of states which will be introduced into the current set of states after doing that action. So one of them would be empty-handed. So if after you enact this action, putting down the pot, you will be empty-handed. You'll no longer have anything in your hand. So that's an added state into the current state space. They could have another one, maybe that, I don't know what else. Probably that would be the only one that would get added, is that you're empty-handed. No longer have a pot. You're also, I guess, 5 pounds lighter, if we want to go that complicated. There's many things you could add, and this complexity of like, okay, what could we actually add? What would be the change in state by dropping the pot? Well, there's, depending on how complex you want to be, there's a ridiculous amount of state changes that you could probably add. And seeing as these state changes are represented discretely, like the individual parts of the action is like each thing you need to say, okay, there's this state, there's this state, there's this state. You can see how a combinatorial explosion would occur. So you've got the current state space. That's what needs to exist before you can do the action. You've got the add list, which would be the states that become part of the current state space after you've done the action. You've also got the delete list. So these are the states that are no longer in the current state space after you've performed the action. So the most obvious one would be holding the pot. So before you were holding the pot, that was an action. That was a state that needed to be active before you could perform the action. But after you perform the action, you are no longer holding the pot. So the process of performing that action would involve the loss of the state holding the pot. So that's a sort of a short rundown. And to reiterate again why this is so bad is that there's quite a lot of combinations of states, and the more actions you introduce, the more add states, the more delete states, the more current states, it just becomes too too complex for the algorithms to process. It just becomes a really bad idea. So I'll just get to now working through the algorithm. Okay, before we start the code, it's important to realize that what this algorithm is going to do is start at the goal states. So assume the goal states and then try and work backwards to see if we can get to the original current state space. And if there is a path that leads from the goal states to the current state states, we'll say that there is a solution for that problem. So we're going to have our initial state, which is the current state space, where we're sitting at the moment. We have the goal state, which is the set of states we want to have at the end, and our operators. And our operators, what I described before, they're the things we have an action, they have an add list, which is the states that they add into the current state space, and they have a delete list, the states that they take from the current state space if they exist. So first of all, we're going to try and track which operators have been applied, and what we're going to do that is by adding a special type of state into the add list. And this state is basically just going to trace what actions are applied. So we're going to add a prefix, which is we're going to say we're executing this action. So whenever we apply an operator, all the states from that operator's add list will go into the current state space. So one of those states will be this executing state. So at the end, we'll print out every state that has the executing at the start, and we'll be able to see which actions were applied. Otherwise, we'd have to sort of trace this thing another way, but this is a super simple way. So for the operator, we're just looking up the add list, and then we're going to append another action. So I'll just show you what the structure of the operator is. Copy it back into here. So we've got the action, which is what's going to happen, what we're going to do. We've got the preconditions, which is what needs to be in the current state space before we can apply the action. We have the add list, which is what goes into the current state space. And we have the delete list, which is what goes out of the current state space. So that's just in JSON format, super simple. All right, we can continue. So this is a short little function. So we're going to go final states equals the achieve all function, which will be defined later. And into the achieve all, we're going to pass in the initial states, we're going to pass in the operators, and we're going to pass in the goal states that we're looking for. And we're also going to pass in an empty list, which is the goal stack. And I'll explain a little later why we need to pass in the goal stack. Okay, and then we're going to ask the final states. If there's no final states, we know that we've failed. So that's very straightforward. We only want to return what we were executing. So we're going to filter all those final states because it's going to retrieve the final states, which are the goal states, and it's going to return a bunch of executing states, which we've added into the add lists. So we're going to filter through all of the return final states. We're going to find the ones that start with executing, and those will be the operators which were applied and the order in which they were applied to achieve the goal we've asked for. So that's just a simple, string dot starts with prefix string in Python. It's a list comprehension for those who aren't familiar with Python. So that function's done. That's just the main driver. A lot of the complexity happens in these other functions, which we define a little later. The next one we're going to find is the achieve all function that we saw called in the GPS function. Okay, so achieve all. So like we said before, this takes very similar arguments to the GPS. It takes all that information, and also takes the thing called the goal stack, which is basically the goal stack is what are we currently trying to achieve. There's a recursive sort of feature to this algorithm. So certain goals will be trying to achieve in the process of achieving the one we're currently achieving. And we'll see how that happens a little later. So this is just, I'll explain. So we've got the states argument is the current active states. The ops argument is the full list of all the operators. So that we need to have at all times a list of all the operators that are available to us. We won't ever pass in a subset of them. We have the goals, which is the set of goals in our goal state, in our achieved final set, and the goal stack, which is the goals we are trying to achieve currently. Okay, so let's start this function up. first we're going to try and achieve each goal individually from that goal list. So if we can't achieve any one of the goals in that goal list, we can't achieve what it's asking for, which is the set of them. So we're going to ask for goal in goals. States equals achieve states, passing in all the states, passing in all the operators, passing in all the goals, and we're passing in the goal stack. So we have the achieve all function is going to call another function achieve, and the role of the achieve function is just to achieve one goal. So in a sense, the achieve all function is a wrapper around this achieve function, which asks achieve all of them. If at any time you don't achieve one of them, then just return none, we've failed. So hopefully you'll get, for every single achieve function call, you'll get a set of states received back, which will be the current state space. And if you're getting a current state space received, that means like, we were successful in trying to achieve that goal. And now the next thing to do is this: we have to check ourselves. We have to check that in the process of achieving one of the goals in the list, we haven't removed any of the other ones. This is called the prerequisite clobber's sibling goal problem. That doesn't really tell you much about how it works, but I'd recommend you look it up on Google, Wikipedia, or whatever. So basically what we're going to ask now is, if any of the goals aren't in the last state space that was returned to us, then at some point we had a goal remove another goal, and thus we've basically hit a wall, and we'll return a failure. But if we haven't had that problem, now we can return all the states. We were fine, we were successful. So let's define this achieve function that was called by achieve all. So this again takes all the states, it takes all the operators, it takes the goal, one goal that we are trying to achieve, and takes the goal stack. So let's just say that the arguments are all the same for this function, except we are taking one goal, not all the goals. And now this function is actually going to do the calling of the last function, which is the apply operator function. And then that does something interesting. But first, let's see how this function works. For those of you Python beginners, just notice that like these strings that are getting put just below the function declaration are just called doc strings. How useful to include those in all your functions. So if goal in states. So what we're doing here is saying, okay, you asked me to achieve one goal. If the goal itself is already in the current state space, then there's nothing to do. So we'll just return the states, we're already done. If the goal is in the goal stack, this is something interesting. The goal is in the goal stack, which means we've previously tried to achieve this goal, and now we're asking to achieve it again, which means that in the process of achieving that goal, we've come up against the fact that we have to achieve it again. So that's circularity, and you don't want to go into a circularity because your function will never return, and we're stuffed. So basically, if we find a circularity, which we will assume that we can't fix this problem, it's impossible. And if we have either of those checks pass, now we reach into the for op in operators. For each operator, we're going to try and attempt to use it. And the first thing to look for is the goal in the operator's add list? If the goal is in the operator's add list, then the operator is useless to us, so we'll just continue. If it is in the operator's add list, then we will apply the operator, and this actually won't apply the operator if it fails. So the operator can return none, and if it returns none, that means that there was a failure. But if it does return a set of states, which again the result is the current state space, then it worked. We could have successfully applied that operator, which means we've successfully added that goal into our current state space. So we'll just return the current state space from achieve, and that will have basically altered the current state space so that we have a bunch of states, one of which is certainly the goal we were trying to achieve. And now this is the last function, define apply operator. This takes the one operator, the set of states, a set of all operators that we have available to us, the goal, and the goal stack. So now this is like what's going to happen if we take one operator and try and apply it to our current state space. This has another recursion. This function itself is going to call another one of the ones previous. So there's this sort of like interlinking of these seemingly like they're pretty simple functions to try and achieve what is essentially a graph search. Like we're trying to search the state space of all operators and all states and see if there's a combination of operators we can use in certain order to arrive at this desired current state space, which is the goal set. Okay, so to apply an operator, we've just got to finish that. Result equals achieve all. So this is interesting. Now we're gonna recall the achieve all function. So we're going to, before we can apply the operator, we have to have all of its preconditions satisfied. So what the achieve all is going to do is it's going to try and achieve all of the operator's preconditions. And if we can do that, then we can apply the operator. If we can't do that, then we can't apply the operator. Therefore, we will return none. And also, we're basically, this is the interesting, we're appending to the goal stack that you see at the end there of the achieve all call, the goal we're trying to achieve. So because we're making this call back to the achieve all function that was originally called in the GPS function, we need to add a goal to the goal stack. And if it didn't return none, we have now this add list, delete list. That's basically the operator's add list and the operator's delete list. It's just a renaming. And we'll ask for state in if result, state for state in result, if state not in delete list. So that takes all the states in the delete list out of our current state space. And we'll also add the add list into the current state space. So that's a list comprehension plus a list concatenation in Python. And it should be very easy to read. So what that is, it's just updating the current states by removing the delete list and adding the add list. And this is the end of all the code for this function. Hopefully, looking through it, it is a little clearer. It'll probably take, once you've typed it out, a little longer to work through and see how all these things are cooperating. But it really does work in this sort of like top down and then like flicks back up. The final function apply operator is referencing again the achieve all function to try and achieve its preconditions, and then by the end of it you should get a working GPS program, which does something that's interesting historically but is not at all very useful for solving problems using today's technology. We have far better ways of dealing with this sort of thing. Okay, so now we can just show the algorithm working. So this is I just ran the algorithm just then, and you just see the list of actions pop up. So we first execute push chair from door to middle of the room, executing climb on chair, executing drop ball, executing grasp the bananas, and then execute eat those bananas that you've just grasped. And we're done. That was the goal too, was the eat bananas. So just show, walking through all the operators, how this was actually achieved. So the start list is at door, on floor, has ball, hungry, and chair at door. At the top, those are the start states, and the finish state is not hungry. So first we want to push chair from door to middle room. So first we have to see chair at door. Oh, this is a disaster.